In the previous couple of videos, we discussed performing the unshift operation, which basically used for adding the node in front of the single linked list, right? That means that in front of the existing head node of the single linked list, we are trying to add a new value or new node with the help of a unshift operation. Now in this video, let's try to understand a function which basically removes the node in front of the single linked list. That operation is nothing but the shift operation. So as part of the shift operation, what exactly we will do is we will basically try to delete the very first node that we have on the singly linked list. That means that we will try to delete the node that is available at head of the singly linked list. Okay, so that is the purpose of the shift operation. Here we will not be taking any arguments from the user. In the end, we will simply return the node that we have removed. That means that whatever the previous head node that we had, right, that we will return as a output. Okay, that is the functionality definition. Now let's just see what all are the different cases that can occur when we try to implement the shift operation. Obviously, the first scenario that could come is basically the singly linked list is empty. That means that there are no nodes at all on the singly linked list on which we are trying to perform the shift operation. And we know how can we check if the singly linked list is empty or not, right? We have made a separate video for that. If you haven't checked it out, you can check that out. But anyway, we know how we can basically check if the singly linked list is empty. If it is empty, obviously, if the singly linked list is empty, how can we actually delete the very first node, right? And head and tail will be at null or none based on our programming language that we are using for implementation, and length will be at 0. So obviously in this case we will not be able to perform shift operation or the removing the first node in the singly linked list. So we will simply return null or none. Okay, so that is the first scenario. And the second scenario is basically where we have only one node inside the singly linked list. If we have only one node in the singly linked list, right, we will have both head and tail node at the same node. That's why we have to make sure that whatever the only node that we are having, that itself we are deleting. That means that singly linked list is becoming empty. So to represent an empty singly linked list, what we will do, we will assign head and tail both with null or none. That's why here if we have only one node, update head and tail both with null or none. So null is basically for the people who are using Java or JavaScript, and none is for the people whoever is using Python for implementation. Okay, so that is something that we have to remember. Along with assigning, what we have to do, we have to make sure that length also we are updating it with 0, because whatever the only node that we have, we are deleting that. As a result, single linked list becoming empty, which is nothing but 0. The length has become 0. Here, before assigning null, you can actually read the head node, because in the end we have to return the node that we are deleting, right? So just for returning that node, before assigning head and tail and length with the appropriate values, make sure that you are reading the head value, so that in the end you can return that value, return the value of head, or you can return the node itself. Okay, that is based on your choice. Okay, this is the first scenario where we have only one node, and the third scenario is obviously greater than one node inside the singly linked list. In that case, what exactly we will do is we are trying to delete the very first node inside the singly linked list, right? So we basically have the impact on the head reference that we are maintaining inside the singly linked list, because whatever the node that is at the head, that itself we have to delete. To delete that, what we will do is whatever the next node that is there after the current head node, that node we will update it to the head of the singly linked list. In this way, we are basically losing the track of the previous head that we are having on a singly linked list. So simple operation, simple assignment operation. Here we have to delete the node that is at the head. That's why we will make sure that whatever the next node that is there from the current head, we will simply update that to head of the singly linked list. Because we are maintaining head and tail of the singly linked list, our head will be pointing to the node that is at the second position basically. In that way, from head to tail we still have the singly linked list, and whatever the node that was there previously as a head, that will get deleted. Okay, so that is the algorithm for removing the or performing the shift operation when we have more than one node. What we will do, we will simply update the head to the next of the head node dot next. Okay, that is something that you can simply do using a simple assignment operation. Along with that, we have to make sure that since we are deleting one node from the singly linked list, we have to make sure that we are decrementing the length by 1. So length will be length minus 1. Okay, so that is those are the scenarios that could come when we try to remove the very first node of a singly linked list. Okay, now let's just try to write the pseudocode for shift operation. Okay, so as part of the shift operation, our aim is to delete the very first node that we have on the singly linked list. Obviously here, what we will do, we will write a function called shift, and this function will not take any argument because it knows that it has to delete the very first node in the singly linked list. That's why we will not take any argument. So as part of the first check, what we have to do, we have to check if the singly linked list is empty. If at all, if the singly linked list is empty, we will simply return null or none based on the programming language that we are using for implementing. Okay, that is the first scenario. And the second scenario is basically we have only one node. That means we know the length of the singly linked list, right? Whatever the length that we are maintaining, if it is equal to 1, that means that singly linked list has only one node in it. Otherwise, the other comparison that you can do is basically if you have only one node, we will make sure that both head and tail are pointing to the same node, right? So the other comparison that you can do is head is equal to tail also you can do, because both will be at the same point, at the same node. As a result, they will match. But I tend to use the length based comparison for checking if the singly linked list has only one value or not. If at all, if we have only one value, what we will do, whatever the head node that we have, we will update it to null/none, and similarly we will also update tail node to null or none. Here one thing that you have to remember is none is for the people who are using Python for implementation, and null is for the people who are using Java or JavaScript for implementation. Okay, so that is something that you just have to remember. Anywhere I am using null or none, it is for the specific people, whoever is using the respective programming language like I mentioned previously. Okay, after updating head and tail, we will update length to 0, because whatever the only node that was there on the singly linked list, we have deleted that. As a result, the singly linked list has become empty. As a result, the length will be 0. So this is the case where we have only one node in the singly linked list. Now let's just try to handle the otherwise case where we have more than one node in the singly linked list. In that case, like I mentioned previously, what we will do, we will simply update the head with the whatever the next node we have from the existing head of the singly linked list. This is the head node and this is the tail node. Let's assume that we have 3 nodes on a singly linked list and we have to delete the very first node. So we will, if we want to delete, we will simply move the head to the next node. In that way, we will lose this, the head that we had previously. That's why we will simply update head with the head node dot next. Okay, and we have to make sure that we are decrementing the length also by 1. Okay, so that is something that you have to remember here. And couple of people, what exactly they will do is, here we already had the next node on the previous head, right? To make that also null, first what exactly they will do is they will read the current head is nothing but the head, right? Now on this, after updating the head node, what exactly they will do is they will also set current head dot next to null or none. Okay, so this is some optional operation, you don't have to do it, but just some people are very particular about updating the next to null or none based on our the way we are implementing. They will make sure they try to update the next of the whatever the head node that we had previously, because in the end we have to return the node that we are deleting, right? That is nothing but the current head. If we simply return the complete head, the complete node, using the next, user still has a possibility to traverse the remaining singly linked list. So they just don't want to give that functionality. As a result, before returning that value, they will make sure that they assign next to with null or none. In the end, we will simply return whatever the current head that we have inside the current head variable, which will basically have whatever the value we had at the head node in the singly linked list. Okay, so that is the implementation of a shift functionality on a singly linked list, which is basically used for removing the very first node we have on a singly linked list. Okay, now that we have written the pseudocode, let's go ahead and let's try to write the programmatic implementation of that. For that, inside the singly linked list implementation class that we have written, right, in that I'm going to add a new function called shift, and it will not take any arguments, because as part of the shift operations we are trying to delete the head node in the singly linked list. So whenever you are trying to delete a single node from the linked list, right, there could be three scenarios. One is either you are trying to perform this shift operation on a empty singly linked list, and the second scenario is you are trying to perform this shift operation on a linked list which has only one value, and the third scenario is you are trying to perform the shift operation on a linked list which has more than one node in the singly linked list. If you can write the implementation for these three scenarios, you are all sorted, and you will be able to delete the head node, and you will be able to modify the head node to the next node of the singly linked list very easily. So let's try to write the Python implementation for these scenarios one by one. So as part of the first case, what I will do, I will write the logic for performing shift operation on a empty singly linked list. So when will we know if the linked list is empty? Either head or tail is null, and or the length of the linked list is null. So previously we have already implemented comparing head or tail to none, right? Now let me go ahead and use length also, so that we would have used that approach as well. So what I will do, I will simply take self.length. I will check if it is 0. That means there are no values in the singly linked list. If this is the case, obviously since the singly linked list is empty, we will not be able to delete the nodes since there are no nodes at all. So I'll simply return none from here. Okay, this is the first case. Otherwise, that means if there is only one node, how will we know if there is only one node? That means both head and tail are pointing to the same node, or if the length of the linked list is 1. So I will go ahead and use length based comparison here. So I will simply compare self.length. If it is equal to 1, then there is only one node in the singly linked list. So what I will do, I'll simply take the value of the current head node, so that in the end we can return it, because we are trying to delete that node itself. So if we delete the only existing node in the singly linked list, obviously head and tail will become none and the length will become 0. So let me update those references. So I'm updating the head to none, I'm updating the tail also to none, and I'm making the length also to 0. Okay, we have successfully made the linked list empty. That's how we are actually deleting the only existing node. Now we simply need to return the node that we have deleted, which is nothing but current head. Okay, or you can, even if you read self.tail also, it will yield the same result, because there is only one node and both head and tail are pointing to the same reference. Now we have successfully written the code for two cases. Now we need to write the logic for the third case where we have more than one node in the singly linked list. In that case, what we need to do, we need to move on to the next node of the current head node, and we need to make that node as a new head node of the singly linked list, so that we will be able to perform any of the operations from head node to tail node once again. So for that, what I will do, I'll simply create couple of variables called current head. I will get and assign head node of the linked list in the beginning. Along with that, the new head node will be the next node of the current head node. So current head dot next. So once this is done, we need to make this head node variable as a new head of the linked list, right? So I'll simply make self dot head equal to new head. And we need, even if you update the current head dot next to null or not, it really doesn't matter, because singly linked list has traversal is possible in only one direction, right? So even if you update the current head dot next to null or not, it really doesn't matter. But since we are going to return this value, it's very possible that user can traverse the entire linked list if you don't set it to null. So that's why I'm setting it to none here. Current head dot next, I'm assigning it to none. Okay. At the end of the day, we are basically deleting one node from the singly linked list. So the length will reduce by 1. So self dot length equal to self dot length minus 1. Okay. And we need to return the deleted node, which is nothing but current head that we have deleted. Okay, in this case, what we exactly did, from the current head node, we have went to the next node, and that next node we've made the new head node, so that we can use this head node and the existing tail node for the further operations that we are going to perform. And we are maintaining the consistency across the singly linked list by doing so. And we are simply making the next of the old head to null, so that we can return the value or the node that we have deleted, and we are returning that current head. Okay, this is how we basically implement the shift operation. Now let's try to execute it and see if the results are matching with our understanding. So let me just remove all this here. Okay, now what I will do, or let's just simply comment out this. Now let's on the singly linked list object, let me just call the shift operation. Okay, if you observe here, we have 4 values in the linked list. First value is 10, that is head is 10, and the tail is 10.10. If we perform the shift operation, basically we should delete the node 10. As a result, the new head of the linked list will be codingpal.arg, and the tail will be 10.0 only, and the output is codingpal.arg true and 10.10. If we execute this from the terminal, so if you see this output here, we have got codingpal.arg true and 10.1 as part of traverse function, and as part of the print statement that we have here, first we are printing the head value, right? That is codingpal.arg, which is perfect, and the tail is again 10.10 only, and the length is 3, because we have 4 values in the linked list and we are deleting one value, which is yielding a singly linked list of length 3. Okay, similarly, if we try to perform the shift operation on a singly linked list where we have only one node, right? So the head and tail are both pointing to the node with value 10 only, so we need to delete that. So basically here we are trying to read the dot value, right? Dot value is not possible, so ideally head should print none and tail should print none, and length should be 0 here. Okay, so we've performed the shift operation, we have printed this separator, and traverse, because there are no nodes at all, we have got it did not print anything, and again we've got one more line separator, and head is none, tail is none, and length is 0. Similarly, even if you try to perform the shift operation on a singly linked list where we don't have any nodes also, we should see the same result here. If I execute it, I get the same thing, because as part of the first condition itself, we are not doing anything, we are simply returning the value. Okay, so this is how we exactly perform the shift operation, or deleting the very first node in the singly linked list. Okay, now that we have implemented the shift operation on a singly linked list, let's just try to analyze the time complexity and space complexity of the same. So you might be wondering, what is the best case and what is the worst case of implementing the shift operation, right? When we try to perform the shift operation on a singly linked list, there will not be any best case or worst case, because we are trying to delete the very first node on the singly linked list itself. Because even if the singly linked list has n number of nodes, even if the singly linked list has only one node, the operation is very similar. When we had only one node, we will simply update the head and tail and length with appropriate values. Even if we have more than one node, or even if we have n nodes, we will simply update the head node to the next of the current head that we are having. So obviously, be it the singly linked list where we have only one node, or be it the singly linked list where we have n number of nodes, we will simply delete the very first node by using the simple update operations. As a result, the time complexity will be order of 1 only. Okay, so now let's talk about the space complexity involved in performing the shift operation. So if you remember, we have basically defined a variable called current head, right? Where we tried reading the head node. Besides this read operation, and we after this read operation, we have basically updated the head node with the head node dot next that we already had inside the singly linked list. The only memory that we are consuming is for this variable where we are trying to read the head node, so that in the end that node is getting deleted, right? Basically we have to return in the end. So obviously that variable will take only constant amount of memory. And even if you take the scenario where we have only one node also, we are updating the head, tail and length that we are maintaining. We are updating it with the appropriate values with null or none and 0. So those update operations will take only constant amount of memory for implementation, right? So even if the singly linked list has only one node, even if the singly linked list has n number of nodes, whatever the shift operation that we are trying to perform will take only constant amount of space for implementation. Okay, that's all there is in terms of time and space complexity analysis of a shift operation on a singly linked list. Okay, so thanks for watching. I'll see you in the next functionality implementation.